Hi, good morning. My name is Janet D'Souza, and I'm a student of the Off-Campus University of New England. And I'm here to do the presentation on one of the most beautiful organs of the human body, which is the eye. So, yeah, I'm going to do the presentation with the help of slides, and hope you enjoy it. All right, so the muscles of the eye. Now, we have about six muscles which are very important, and they're the ocular, the word eye. So we have the superior, the inferior, the lateral, the medial, and those are the rectus muscles, which is more outside, so that's why the word rectus. And then we have two oblique, which go this way, and we have the superior and inferior for that as well. Now the nerves, coming to the most important nerves that innervate these muscles. So we have the six cranial nerves now, and the most important out of them, the optic nerve, the oculomotor nerve, trochlear, trigeminal, abducens, and the facial nerve. These nerves are very, very important for all the movements of the eye, up, down, in, out. Yeah, like when you read the paper. You need to surf from left to right. You need the trochlear and the abducens for that. And then going downstairs, the eyes have to be down and in. You need the oculomotor for that. For vision, you need the optic nerve. So they're all very, very important. Now, these nerves also have something very special, as in the reflexes. Reflex is something like when you touch or when you feel something, a response from the body. So that goes in two mechanisms. We have two sets of neurons for that. The afferent, which takes impulses from your skin or from the organs, and it takes it all the way to the brain. So that is afferent, which goes from the body to the brain, which comes down from the brain to the body, any part of the brain, be it the cerebral cortex or the medulla, the corpus callosum, any part of the brain, to your body, like in your muscles or your glands, and to elicit that response or to give that response back. That is the efferent nerve. So there is something very interesting in the nerves. Now, if I look at the optic nerve and the oculomotor nerve, they are known for the pupillary reflex, which is the torch. If you take a torchlight and say you shine it on my right eye, that was the afferent thing, wherein you try to stimulate a response. The optic nerve has taken it, the right optic nerve has taken it. And how does it respond? Both your eyes, the right and the left, they constrict. That constriction is the pupillary reflex. Now, had it not been that the eyes constricted, then there is a problem with your optic nerve, which took the sensation, but the oculomotor nerve was not able to give the sensation out, right? So your eyes did not constrict. Likewise, if I have the fifth and the seventh cranial nerve for this example, where the fifth one is the trigeminal and the seventh is the facial nerve, they have something called the corneal reflex. Now that is when I take a cotton bud and just put it in your eye, say any eye, what is the reflex going to be? Like, what is your response? What is the body's response going to be? If there is any wind, heavy wind, and you're out and it's blowing onto your eyes, onto your face, you immediately blink, right? So likewise, when your corneas are touched by the cotton bud, you will blink your eyes. So what was taken was afferent, and that was taken by the trigeminal nerve, the fifth cranial nerve, and what response was given in the sense of blinking was done by the facial nerve. So that was the fifth and the seventh nerve. Now, moving on to the chambers, we have two chambers, the aqueous and the vitreous. Now, the aqueous chamber is what keeps our eyes moist, like it's nice and lubricating and there's a shine, your eyes are not dry, and that is because of the aqueous humor. Now, this has got a low protein called the ciliary epithelium. The word cilia itself means hair-like cells or hair-like projections which move. So they help to move this low protein that drains to the canal of Schlemm. And if it's blocked for some reason, if this is blocked, what happens? intraocular pressure in the eye increases, and that intraocular pressure increasing leads to dry eyes, leads to glaucoma, eventually leads to blindness. It's always important to keep your eyes moist, and this is done by the aqueous chamber. And if they do not, then we have medication, eye drops. Especially diabetes is one of the conditions wherein you can have dry eyes. And now the second chamber is the vitreous humor. This is a gelatinous matrix which gives the shape of the eyeball. Photoreceptors, very, very important. They are specialized neurons which are found in the retina that convert the light that gets into your eyes, convert it into electrical signals which stimulate physiological responses, right? So it's vision, like you need the light to be taken by your eyes to be, then passed on to your higher center, which is the brain, to give you that signal of vision. So signals from these photoreceptor cells are sent through the optic nerve. So we have a nerve now through the optic nerve to the brain for processing. So that's the retina. And then when the light falls onto the retina, here are all the cells we have, the photoreceptors right on top here. And then from the photoreceptors, it goes to the bipolar cells, from the bipolar cells to the ganglion, from the ganglion to the optic nerve to the optic disc. And that is how we see what we see, thanks to all these cells. Now, when light hits the retina, very important, when light hits the retina, retina is a light-sensitive layer of tissue which is at the back of the eye. Special cells called the photoreceptors that we spoke about turn the light into signals, electric signals. These electric signals then travel from the retina through the optic nerve to your brain. So the brain turns the signals into images that you see. Now the images again are upside down on the retina, but then again the brain processes it and you see it straight. Imagine seeing everything mirror image. Not happening. That would lead us all into depression, right? So vision is the most important. Very important also the surface. Now if it's a concave surface, like concave is more cave-like, there's a lot of surface. If the light falls on a concave surface, what's going to happen? It's going to diverge. It's not going to converge, it's going to diverge. So which means concave is good for seeing things that are far, not things that are close. For things that are closer, we need convex lenses which converge. The name is so convex, converge, C-O-N-V-E, so converge, yeah? Now parallel light rays that pass through the concave lens do not meet. Like I said, they diverge, right, if it's a concave. So concave lenses are used to correct nearsightedness. Nearsightedness in the sense you can see near things, you cannot see far things. And a concave lens in this case corrects myopia by being thinner at the center, thicker at the edge. So with this, the light that is there now, it lands directly on the retina instead of the front of it. So it's kind of on the retina or behind the retina, but not in front. Okay, but convex lens, they help in farsightedness, like in the sense when you can see something far, you cannot see something close. That's when you need your convex lens. So that explains that. Hyperopia. This is a condition in which the image of a distant object becomes focused behind the retina. Like I said, the farsightedness. You see far, you can't see close. We spoke about myopia. What is astigmatism? Many people are born with astigmatism. What is astigmatism? It's something with your lens, the curvature of your lens. Now, when this curvature is not concave or convex, you have a mix. Like you can see or you cannot see, you cannot see. You see distorted images, but you cannot see far well, you cannot see close well. So there's a problem with both. And that is the problem because of how your cornea is shaped. Now, wavelengths. Wavelengths shorter than 400 or longer than 700 is not captured by your eye. Only between 400 to 700. Nothing lesser than 400, nothing greater than 700. And there are these bees who can see above 700, and those are ultraviolet. Also bats, yeah? Remember studying about bats and their vision? That's why they are more at night and nocturnal, so they can see that vision. Photoreceptors are two kinds, the rod cells and the cone cells. The word rod, so much like a rod, it's stiff, so you cannot see during, they are not active daylight, they are active at night. Maybe Draculas have more of the rod cells, I'm assuming. Maybe even if there's such a thing as a Dracula. But cone cells, they give you color. So thanks to cone cells, you can see the colorful world because of the cone cells. Now, the rod cells, something very interesting. During the night or when there is darkness, there is a cyclic GMP and CNG which is high. So because of this, an action potential is generated wherein the sodium influx is more. And when the sodium influx is more, the cells get depolarized. So here the rod cells get depolarized. Glutamate is released then to the bipolar cells. So this glutamate works in the darkness and it's released to the bipolar cells because, like I said, from the photoreceptors it goes to the bipolar cells. Now, bleaching is recovery or slow adaptation of eyes from bright to dark. Now, when you immediately go from a bright environment, go to a movie theater, which is all dark, it takes time for your eyes to adjust, right? That's why we have people with torches and everything around to get you to your seat if you reach late. But if not, people being around, you use your phones these days. Yeah, so that's bleaching. It's a recovery. Now again, bipolar cells are of two types, the on cells and the off cells. So the on cells, they work during the light. The off cells are more active during the night. So on-center bipolar cells will depolarize, whereas the off-center bipolar cells hyperpolarize. So this arrangement helps provide a spatial processing of the visual input derived from the photoreceptor cells. On-center bipolar cells are depolarized by small spot stimuli positioned in the receptive field center. Receptive field. So there is a field of vision that's called. Off-center bipolar cells are hyperpolarized by the same stimuli. Both types are repolarized by light stimulation of the peripheral. So this is peripheral. It's not in the center but outside. Yeah, the peripheral vision that we talk about, thanks to the bipolar cells, the on and the off cells. That's there. Now, the on-center GC cells, they produce more action potentials when stimulated by a bright light in the center and are inhibited by stimuli on the surround. So more in the center, inhibited by the surround, that is the periphery. Off-center GCs are stimulated by surround and inhibited by the center. So that's how the on and off cells work here. As we can see, this is the light source, this is the light source, and then here, the on bipolar, they get depolarized in light. Off bipolar get hyperpolarized in light. That is, they stay kind of inactive. The off, they stay inactive in light. The on are more active in light. And they need two receptors, the metabotropic receptors and the inotropic receptors, which I shall talk briefly. Okay. If the light is on, the bipolar cells, they release a receptor called the metabotropic receptor, which is called the GluR6, that hyperpolarizes when the glutamate increases. So it's not very happy when the glutamate increases. So it kind of hyperpolarizes, kind of going into hibernation sort, yeah. And when it is not activated, like when this glutamate is not activated or when the light polar cells are, in that stage of hyperpolarization, you can see in the dark. But when it is not activated, the on cells are depolarized, because what is not activated? It's not activated in the dark. That's when it's not activated. So the on cells then get depolarized. Off cells, the bipolar off cells, have an inotropic glutamate receptor. Over here for the on, we had the metabotropic receptor. Here it is the inotropic receptor. Now these, they depolarize in the dark and repolarize in the light. Simple. We need cells to depolarize in the dark and cells to repolarize in the day, and vice versa. So if something is depolarized during the day, it gets hyperpolarized during the night. Easy? Bipolar input also comes from horizontal and amacrine cells. They also help, but the most important focus for us here is going to be the bipolar on and off cells. Ganglion cells are the projection neurons of the vertebrate retina, conveying information from other retinal neurons to the rest of the brain. So it doesn't just end here. The story still continues. What happens when your ganglion cells are decreased, or say in surgery by mistake? in error or accident, something, that just depletes your ganglion cells, or your ganglion cells are just removed accidentally. It decreases the visual function, of course. So what visual function? The center or the periphery? Like we discussed, incremental loss of peripheral, not central. For the central vision, we have the fovea. And the fovea is one part now that does not have blood vessels, doesn't have any cells. So all the light, the majority of the light is there. Sorry about that. I guess I went a little over time, but I still would love to continue this. So I was at the fovea, and the fovea is that part of our eye which captures the maximum light. And again, this fovea doesn't have many blood vessels in it, so it can focus all the light that comes in, which is why we get the accuracy or the central vision, and that happens because of the fovea. So if your fovea were not there, you wouldn't have had the center vision, you would have had the vision of the periphery. On the contrary, you don't have your ganglion cells, you don't have the peripheral vision, because they are important in peripheral vision. Now I said that the optic disc, because it does not allow, it just does not allow the light rays to get into the retina. So because of that, you have this slight, not really a problem, but this can pose a problem when you're driving or, on the bike. Yeah, that is, you cannot see things farther from your peripheral vision, and that creates a blind spot. So you'll have to turn your neck or head every now and then to look at the ongoing traffic because of the blind spot. Most important, and the last most important segment here, is the optic chiasm. So if you can see, these are your eyes, the left eye and the right eye. And here, this is a part where the left crosses and goes to the right crosses and goes to the left. And that is your optic nerve. So this is the optic nerve which does the crossing, and they do the crossing at the chiasma. So, or chiasm, whatever it's called. So now, if this chiasm, for some reason during surgery, or if there's a tumor and that presses on, it gets larger and it presses here, right at the center, what's going to happen? You will not have any peripheral vision. You're only going to have this part of the vision. So which means it's going to be a tunnel vision. You're not going to have the peripheral vision, which here is where I'm pointing out. In the case of a left retina, right retina, that would be your peripheral vision. So that would be cancelled out, and only this part you would be able to see, and that would be the tunnel vision, which is everything in front but nothing on your sides, and that's the tunnel vision. Likewise, if you can see from here, there is the temporal and the nasal vision. So the left retina has, like here, it'll be the left temporal and the right nasal, and vice versa in the case of the right retina. So when we have cerebrovascular accidents or stroke, now if it is the case of left retina which is damaged, you will have the right side where is affected, and the right side in the sense you will have the right hemianopsia. So in this case you will have right temporal, but you won't have the left nasal vision. Sorry, the right temporal, but the right nasal will be blocked. Yeah, so right temporal is good, right nasal is blocked. So this becomes a problem with strokes. But otherwise, all said and done, if there is a tumor and that affects this area here, you can only be able to see the central vision. And that central vision is called the tunnel vision. So just imagine, you just see things straight. You cannot see anything on this side. This is the fantastic journey of the eye, and we must be grateful to every organ of our body, especially the eye, because this is something that senses all the information that we receive from our external environment. The first mode of contact with anything from the time we wake up to the time we go to bed, our eyes. So take very good care of them. Thank you.